February 1942, the North Atlantic, 500 nautical miles southeast of Greenland. The water is the color of slag iron. A freezing wind shears the tops off waves, hurling spray across the rolling decks of 70 merchant ships, convoy ON-166, a slow moving serpent of steel and cargo, creaks eastward, in their escort vessels, Allied radio men hunch over their sets, ears filled with the hiss of static and the dread of the voids. They are blind. Beneath the surface, U-201 glides, a gray predator. Its commander, Kapitänleutnant Adalbert Schnee, studies his daily B-Dienst intelligence report, a decrypted Allied signal that has given him the convoy's approximate course. Around him, a pack of a dozen other U-boats, summoned by encoded radio pulses, converges like wolves. They operate with a terrifying confidence, their orders, their positions, their victory reports are all enciphered by a machine they believe to be an absolute guardian of their secrets, the Schlüsselmaschine M, the Enigma. At Bletchley Park, 50 miles north of London, it is 3 in the morning. A cryptanalyst stares at a wall of incomprehensible cipher groups intercepted from U-boat command. He runs a hand over his face. Until yesterday, they could read this traffic. Until yesterday. They could have warned on 166, but on February 1st, the rules changed. The Germans added a fourth rotor to their Naval Enigma machines, the clicks and whirls of the British bombe machines designed to crack 3-rotor settings now produce only silence and futility. The Atlantic has been plunged back into cryptographic darkness. The Allies are losing the war not on the battlefields of Europe, but in a silent, desperate race between two machines, one designed to conceal, the other to reveal, and for now the concealer has won. The story does not begin in the shadows of war, but in the bright promise of peacetime commerce. In the early 1920s, a German engineer named Arthur Scherbius patented remarkable device, the Enigma. Its purpose was to protect corporate and diplomatic secrets in an increasingly connected world. Scherbius's invention was electromechanical. Resembling a heavy, intricate typewriter set inside a wooden box, its genius lay in its apparent simplicity and profound complexity. A user would type a plaintext letter A. An electrical current would flow. It would first pass through a plugboard, a faceplate at the front studded with cables. This could swap A with another letter, say F, before the signal even entered the machine's core. Then it would journey through a set of rotors, wheels inscribed with the alphabet that could be set in any starting position. As the key was pressed, the first rotor would click forward one position, altering the electrical pathway. After a full rotation, it would kick the next rotor forward like an odometer. The current would pass through the rotors, bounce off a reflector at the end, and journey back through them along a different path, finally lighting up a letter on a lamp panel. L, for instance. That L was the ciphertext. The system was polyalphabetic substitution on a scale never before mechanized. With each keystroke, the encryption alphabet changed. The same letter A typed 3 times in a row would produce 3 different encrypted letters. To decipher the message, the receiving operator needed only to set his identical Enigma machine to the same exact initial settings, the rotor order, their starting positions, and the plugboard connections. Then typing the ciphertext L would light up the original A. It was elegant, portable, and for its time, revolutionary. The German military, humiliated by the Treaty of Versailles and paranoid about future security, took notice. In the late 1920s, the Reichswehr and later the expanded Wehrmacht began adopting and refining Scherbius's machine. They added security features. The commercial plugboard was removed. A more complex military standard plugboard Steckerbrett was introduced. They increased the number of available rotors from 3 to 5, then 8, allowing units to choose which 3, or later 4, were inserted into the machine on any given day. The mathematical possibilities exploded into the realm of the astronomical. The cryptographers of the Reich calculated the odds with the correct procedures. Followed settings changed every 24 hours at midnight. secure distribution of codebooks. The machine was deemed unbreakable. They had a point. The theoretical number of possible starting configurations for a 3-rotor plugboard equipped Enigma was approximately 158 million. It was a number beyond human comprehension, a lock of seemingly infinite complexity. By the time the Nazi war machine rolled into Poland in September 1939, the Enigma, in its various Army, Air Force, and most crucially, Navy forms, was the central nervous system of German military communications. It encrypted everything from routine logistics reports to the highest orders from Hitler's Führerhauptquartier. Its clicks and whirs were the sound of a war they believed they could fight in perfect secrecy. Yet, even as the German military placed its absolute faith in this mechanical guardian, a fatal flaw existed, not in its engineering but in human nature. The very arrogance that declared it unbreakable sowed the seeds of its downfall. For the Poles and then the British and Americans, the challenge was not to outmuscle the machine, but to outthink the men who used it. While the German High Command slept soundly behind their wall of enciphered text, quiet, relentless counteroffensive was already underway. It did not begin in Britain, but in Poland. In the early 1930s, facing the rising threat of a resurgent Germany, the Polish Cipher Bureau assembled a team of brilliant mathematicians, men like Marian Rejewski, Jerzy Rozicki, and Henryk Zygalski understood that to defeat a machine, one needed the cold logic of mathematics. Through a combination of theoretical genius, espionage, and sheer intellectual force, they made the first crucial breaches. Rejewski deduced the internal wiring of the Wehrmacht Enigma rotors. They then built mechanical aids, primitive, clockwork-driven devices they called bombas, to help search for daily settings. The Polish breakthroughs were the foundation, a gift of incalculable value. But in July 1939, with war looming, the Poles, realizing they could not sustain the effort alone, invited French and British intelligence to a secret meeting in the Pyry Forest near Warsaw. They handed over replicas of the military Enigma and detailed their techniques. The baton was passed as the panzers crossed the Polish border weeks later. The core of the Allied codebreaking effort relocated to a sprawling, eccentric Victorian estate 50 miles north of London, Bletchley Park. Here, in huts scattered across the muddy grounds, a strange new army assembled. It was comprised of mathematicians, linguists, chess champions, and crossword puzzle savants. They were led by the enigmatic figure of Commander Alastair Denniston. Among them was a young, idiosyncratic Cambridge don named Alan Turing. Turing absorbed the Polish work and then moved beyond it. He conceptualized a more powerful electromagnetic machine to tackle the problem, the British bombe. This was not a code-breaking machine in the sense of thinking like a computer. It was a brute force eliminator. Its purpose was to test thousands of possible Enigma rotor settings per minute, searching for logical contradictions until it found the one configuration that could have produced the intercepted ciphertext of the day. The first Turing designed bombe, nicknamed Victory, became operational in March 1940. But breaking the Enigma was a continuous, not a singular event. Each day at midnight, German operators would switch to new settings, rendering all of yesterday's work obsolete. The process was a frantic daily race against the clock. Furthermore, not all Enigma traffic was equal. The Luftwaffe, using less rigorous procedures, became the first consistent source of decrypts, codenamed Ultra. The Army's traffic followed, but the Kriegsmarine, the German Navy, presented a far more formidable challenge. Under the meticulous, paranoid direction of Admiral Karl Dönitz, U-boat command employed a separate, more complex Enigma system, known to the Germans as the Schlüssel M key M and to Bletchley as Dolphin. Its procedures were tighter, its operators more disciplined. Most devastatingly, its signals were the lifeblood of the Battle of the Atlantic. By 1941, this battle was the war's pivotal struggle. Britain, an island, was being strangled. U-boats hunting in coordinated wolf packs directed by encoded radio signals from France were sinking merchant ships faster than they could be built. The tonnage war was being lost. Each month, hundreds of thousands of tons of food, fuel, and munitions vanished into the icy depths, rationing bit deep. The nation's survival hinged on the Atlantic lifeline. Bletchley's occasional breaks into Naval Enigma in 1941 provided fleeting glimpses of U-boat patrol lines, allowing convoys to be rerouted, but these breaks were fragile, agonizingly slow, and dependent on captured codebooks or operator errors. The bombs, massive cabinets of spinning rotors and whirring drums, were few in number and temperamental. The cryptanalytic war was a knife edge, and in early 1942, the Germans, unknowingly responding to perceived Allied successes, sharpened that edge to a razor point. They introduced a new layer of security, a fourth rotor, for U-boats operating in key areas. The result was not just a new problem, but a return to utter blindness. The three rotor bombs were useless against it. The blackout was immediate and total. The wolf packs, once shadowed, now melted back into the vast, trackless ocean. The slaughter of the convoys resumed with a terrifying efficiency. At Bletchley Park, a cold desperation set in. The theoretical solution, a four-rotor bomb, was understood, but building it at the scale and speed required seemed an impossibility for a British industry stretched to its limits by bombardment and blockade. The Allies needed a miracle not of intellect, but of industrial production. They needed to look across the Atlantic. The battle against Enigma was not fought by faceless institutions, but by individuals whose peculiar geniuses were weaponized against the logic of the machine. On the German side, the operators were cogs in a vast, disciplined system. Their role was procedural fidelity, to follow the codebook, set the rotors correctly, and transmit without error. The true architects, like Scherbius, had long since receded from the story. Confidence in the machine was absolute, a matter of doctrine. On the Allied side, the effort demanded a different breed. At Bletchley Park, Alan Turing was the theoretical spearhead. Disheveled, often absently minded, he possessed a mind that could conceptualize the problem in purely abstract mathematical terms. His 1940 treatise, The Applications of Probability to Cryptanalysis, was a foundational text. He didn't just seek to break a cipher, he sought to model the machine's logic and the operator's habits within statistical frameworks. His bomb design was a physical manifestation of this theory, a machine to automate the search for inconsistency. But Turing did not work alone. Gordon Welchman, a sharp organizational mind, added the crucial diagonal board to the bomb design, dramatically increasing its efficiency. There were the codebreakers in skirts, thousands of women like Mavis Lever and Joan Clark, whose meticulous pattern recognition and intuitive leaps solved specific cribs and nuances that machines alone could not. And in Hut 8, alongside Turing, worked people like Hugh Alexander, a chess champion whose strategic mind excelled at the daily puzzle of menu building, crafting the logical chains the bombs would test. Across the Atlantic, the human angle shifted from pure cryptanalysis to engineering and industrial management. The key figure was not a mathematician, but an electrical engineer, Joseph Desch, at the National Cash Register Company in Dayton, Ohio. Quiet, intense man, Desch was tasked with the seemingly impossible, designing reliable, high-speed, four-rotor bomb that could be mass-produced by factory workers. Not hand-tooled by craftsmen, his genius was in simplification and standardization, translating Bletchley's fiendishly complex blueprints into something that could roll often. Assembly line. His team, working under immense pressure and secrecy, became the unsung engineers of victory, their battle fought with oscilloscopes and soldering irons against deadlines and burnout. This intellectual struggle had its brutal physical expression in the North Atlantic. The tactical dance between the U-boat Wolfpack and the Allied convoy was a direct function of signals intelligence. Admiral Dernitz's Rudel tactic was a masterstroke of decentralized Coordination. U-boats spread across the ocean would report sightings via short, encrypted Enigma signals to headquarters in Lorient, France, Dernitz's staff. The Befehlshaber der U-Boot, BDU, would then vector other boats to form a pack and orchestrate a nighttime surface attack. The tactic maximized terror and minimized the effectiveness of escorts. For the convoy commodore and his escort commander, the ocean was a terrifying chessboard where the enemy was invisible. Their only clues were the crackling reports of HFDF, high-frequency direction finding, HFDF, which could get a rough bearing on a U-boat's transmission, and the sporadic precious ultra decrypts. When Bletchley was reading the traffic, the tactical advantage shifted decisively. Convoy routing officers in the Admiralty's Operational Intelligence Center could divert entire convoys hundreds of miles around known patrol lines. It was a silent, strategic avoidance. When the blackout came in February 1942, the tactical picture reversed. The wolf packs regained their invisibility. Convoys steamed blindly into waiting patrol lines. The escorts, deprived of foreknowledge, could only react, sprinting to the site of a torpedo explosion, dropping depth charges into an empty sea while the U-boat slithered away. The kill ratios plummeted. In the first half of 1942, U-boats sank over 3 million tons of shipping in the Atlantic alone, and less than 1% of all U-boats at sea were being destroyed. The tactical reality was simple, without the ability to read the enemies operational mail, the Allies were losing the Battle of the Atlantic. This tactical desperation is what transformed the American bomb project from a technical assistance program into an urgent, supreme national priority. The solution would not come from a single brilliant mind in a hut, but from the coordinated might of a nation's industrial heartland. The Enigma and the bomb represented two opposing philosophies of machine warfare. The Enigma was a device of obfuscation. Its engineering brilliance was in creating a near infinite maze of electrical pathways. Every component, the plugboard swaps, the rotor's internal wiring, their starting positions, the reflector's unique connections, was designed to diffuse and disguise information. Its security was multiplicative. Each layer of complexity multiplied the possible settings. The four-rotor Naval Enigma, introduced in 1942, was the apex of this philosophy. It added not just a fourth moving rotor, but a thin, non-stepping Greek rotor, beta or gamma, that sat between the reflector and the fast-moving rotors, introducing yet another layer of static encryption. The machine was a black box, signal in, chaos out. Its operators needed no understanding of its internal logic, only faith in its output. The Allied bomb, in contrast, was a machine of deduction. It did not break codes in the sense of solving a puzzle. It was a high-speed hypothesis tester. Its function was elegantly simple in concept, monstrously complex in execution. Cryptanalysts at Bletchley would first find a crib, an educated guess about a piece of the plaintext that might correspond to a stretch of ciphertext. For example, a routine weather report might always contain the word weather. By aligning this guess plaintext against the ciphertext, they could deduce a chain of logical relationships between letters at different positions in the message. This chain was wired into the bomb as a menu. The bomb's banks of spinning, electrically connected rotors would then replicate dozens of Enigma machines running in parallel. It would cycle through possible rotor orders and starting positions at a furious pace. Eventually, the American machines would test over 2,000 possibilities per second. It was searching for a contradiction, an electrical loop that proved a particular setting impossible. When no contradiction was found, the machine would stop. That setting was the stop, a candidate for the day's key. It was then tested on a replica Enigma. The bomb didn't provide the answer. It eliminated the impossible. What remained, however improbable, was the truth. This was a machine that turned the Enigma's internal logic against itself, using its own perfection to find the one flaw of consistency in a sea of noise. This technological duel escalated into an industrial one. For the Germans, the Enigmas. Security was maintained through secrecy and precision manufacturing. The machines were produced in limited numbers by trusted firms like Maschinen AG in Berlin. Distribution was tightly controlled via secure couriers and codebooks printed with soluble ink. Their entire system was predicated on the machine being a static, unbreachable artifact. The industrial effort was in producing and protecting the key, not in constantly re-engineering the lock. For the Allies, the challenge was the opposite. The lock changed every day. Breaking it required an industrial effort of a different magnitude. Initially, Britain's bomb production was a cottage industry of brilliance and desperation. The first machines were built by the British Tabulating Machine Company at Letchworth, hand-wired by a small team working in secrecy. Each bomb was a unique, temperamental beast, requiring constant maintenance by Wren's, Women's Royal Naval Service, with soldering irons. By 1942, there were about 30 British bombs, a formidable effort, but utterly inadequate. Against the four-rotor naval blackout, Britain simply did not have the spare industrial capacity, copper, or precision engineers to scale up production to the required level. This is where the United States entered not just as an ally, but as an industrial arsenal. The US Navy, under the direction of Commander Joseph Wenger and Lieutenant Commander Ralph Meader, contracted the National Cash Register Company, NCR. Dayton, Ohio. NCR was chosen not for experience in cryptography, but for its expertise in precision electromechanical manufacturing, the same skills used to build complex cash registers and accounting machines. Joseph Desch's lab, the U.S. Naval Computing Machine Laboratory, was established in secrecy behind NCR's walls. The American approach was one of radical standardization and mass production, where the British bomb was handcrafted, the U.S. Navy bomb was engineered for the assembly line. Desch's team redesigned components for easier manufacturing, using stamped metal parts and simplified wiring looms. They built specialized tools and jigs. They broke the construction into phases, training hundreds of workers, many of them women, to perform specific compartmentalized tasks. They weren't building dozens of machines, they were building hundreds. The goal was not just to break the four-rotor Enigma, but to drown it in a flood of American electrical current and rotational speed. This was the ultimate expression of Allied war production, treating the abstract problem of cryptography as a tangible production quota to be solved with lathes, wiring, diagrams, and time clocks. The stage was now set for the moment when this vast industrial potential would be brought to bear on the critical turning point of the naval war. The blackout, February 1, 1942. The change came without fanfare, encoded in the very traffic it was designed to protect. On the first day of February 1942, the U-boats of the Atlantic operational area switched to a new system. The three-rotor Schlussel M machines were not discarded. Instead, a modification was issued, a fourth rotor inserted between the leftmost rotor and the reflector. To the operators, the procedure was a simple mechanical adjustment. They were issued new codebooks, Schlüsseltafel M, with columns for this fourth rotor's setting. The machine's internal complexity increased by orders of magnitude. For the listening stations of the Allied Y service, the intercepts continued to flow, endless streams of seemingly random letters. But at Bletchley Park's Hut 8, where the naval Enigma was attacked, the effect was cataclysmic. The three-rotor bombs, with their banks of 36 fast-spinning drums, were rendered instantly obsolete. The menus built by the cryptanalysts no longer fit the new electrical labyrinth. The machines would run, whirring and clicking for hours, only to produce meaningless stops, or more often nothing at all. The four-wheel traffic, as Bletchley labeled it, was a wall of impenetrable noise. The intelligence pipeline from Bletchley to the Admiralty's Operational Intelligence Center, which had been growing in reliability, ran dry. The blackout was total and immediate. In the Admiralty's subterranean tracking room, the large map of the Atlantic began to fill With terrible clarity, HFDF bearings still showed U-boats transmitting, but now their purposes were shrouded, convoy routes, once cleverly threaded through gaps in the U-boat patrol lines now had to be guessed. The guesses were wrong. The month of February 1942 saw shipping losses in the Atlantic surge to over 500,000 tons. March was worse. The U-boats, operating with renewed confidence, enjoyed what they called the second happy time, particularly off the coast of America, where unprepared U.S. defenses offered rich targets. Admiral Dernitz's strategy was working with brutal efficiency. At Bletchley, a pall of frustration and dread descended. Alan Turing and his team understood the theory of the four-rotor brake. They had even begun designing a theoretical four-wheel bomb, but the practical obstacles were immense. Building such a machine required more of everything: more rotors, more electrical circuits, more space, more power, and most critically, more time. Britain, in the fourth year of total war, had none of these to spare. The very factories that might build such machines were building Spitfires and tanks. The copper for its millions of feet of wiring was needed for shell casings and radios. The cryptanalysts were reduced to searching for marginal shortcuts, trying to exploit rare signals still sent on the three-rotor system, or hoping for a catastrophic German procedural error. It was a war of attrition they were losing. The crisis forced a fundamental strategic decision: the intellectual capital of Bletchley Park was not enough. Beating the four-rotor Enigma would require the industrial capital of the United States. In the spring of 1942, a secret diplomatic and technical exchange reached its culmination. Turing himself had traveled to the United States the previous year, sharing bomb designs with Bell Labs and the US Navy. Now, the full weight of that partnership was invoked. Blueprints, circuit diagrams, and the grim urgency of the Atlantic situation were packaged and sent across the submarine-infested ocean. The challenge was handed to Joseph Desch in Dayton, Ohio. The mandate was simple and impossible: design a reliable, high-speed four-rotor bomb, then build it, not one, not 10, but in numbers that could overwhelm the problem. The race was no longer just against the German U-boats. It was a race against the collapse of the Allied logistical lifeline. The turning point of the intelligence war now hinged on the success of an unproven machine in a landlocked American factory, thousands of miles from the gray sinking waters it was meant to save. In Dayton, Ohio, behind the unassuming facade of Building 26 at the National Cash Register Company, a feverish, secret world took shape: the U.S. Naval Computing Machine Laboratory, shrouded in wartime secrecy, became the staging ground for the counter-assault. Joseph Desch, now shouldering perhaps the greatest cryptographic burden of the war, faced a problem of physics, engineering, and scale. The British four-wheel bomb design was a starting point, but it was too slow, too complex, and too fragile for the production lines Desch was tasked to create. His mission was to imagine it for American industry. The core challenge was speed and reliability. To search the exponentially larger key space of the four-rotor Enigma, the bomb needed to test settings at a pace unthinkable to the British. Desch's team, comprising NCR engineers and Navy personnel, made critical innovations. They increased the rotational speed of the bomb's replica rotors dramatically. Where the British machines spun at a cautious 50-60 RPM, the American target was over 1,700 RPM, a blur of spinning brass and bakelite that generated immense heat and mechanical stress. This demanded new bearings, new cooling systems, and a drive motor of unprecedented reliability. But Desch's most significant breakthrough was electrical, not mechanical. He pioneered a revolutionary form of high-speed electronic switching to test the logical menus. Instead of purely electromechanical relays, his design incorporated thyratron tubes, early vacuum tubes used for switching. These could open and close circuits thousands of times faster than a clattering relay, allowing the machine to test for electrical contradictions almost instantaneously as the rotors cycled. This hybrid Electromechanical electronic design was the key to achieving the necessary speed. It was a daring fusion of technologies, and its success was far from guaranteed. The pressure on Desh was immense, the Navy, personified by the driven lieutenant. Commander Ralph Meter demanded results. Reports of soaring Atlantic losses landed. On his desk, security was paranoid. Workers knew only their specific component, Desh. Himself worked to the point of collapse, suffering from stress-induced illness. The first prototype, a towering, 16-foot-long, 7-foot-tall cabinet of gleaming metal. Whirring rotors and intricate wiring, was ready for testing in the spring of 1943. It was known as the Desh bomb, officially the US Navy CSB 2500. The initial tests were fraught, the machines pushing the limits of contemporary engineering broke down, rotors jammed at high speed, thyrotrons burned out. The intricate backlash mechanism, which allowed the rotors to reverse direction without damage, failed. Each setback meant more ships lost, but Desh and his team, in a relentless cycle of testing and modification, ironed out the flaws. By April 1943, the first production models were being assembled not by engineers, but by teams of trained factory workers. The assembly line, a concept alien to British bomb production, was now the engine of cryptanalysis. The first operational US Navy bombs were installed, not in Dayton, but in a newly constructed windowless concrete fortress on Nebraska Avenue in Washington, D.C. The Naval Communications Annex, here, under the command of Commander Joseph Wenger. Waves of waves, women accepted for volunteer emergency service, operate the monstrous machines. The room was a deafening cathedral of technology, the roar of 60 horsepower motors, the high-pitched whine of spinning rotors, the clatter of stop relays. The heat was tremendous. The operators, trained in a rigorous 2-month course, became extensions of the machines they tended, watching for the telltale halt of a rotor bank, then noting the candidate settings to be relayed to Bletchley for verification. In May 1943, the first consistent breaks into the 4-rotor Triton traffic began to flow. From Washington to Bletchley, and from there to the Admiralty, the blackout was not shattered all at once, but pierced, then cracked, then finally lifted. The industrial might of America had been successfully channeled into the most abstract of battles. The flow of ultra-intelligence, the lifeblood of Allied naval strategy, was restored just in time for. In the mid-Atlantic, the climactic convoy battles of the war were reaching their brutal crescendo, and for the first time, the hunters were about to become the hunted. The renewed flow of ultra in the spring of 1943 did not simply allow convoys to be rerouted, it enabled a fundamental shift in Allied tactics, from evasion to annihilation. With reliable, near-real-time intelligence on U-boat positions, courtesy of the American bombs churning in Washington, the Allies could now plot the precise locations of wolf pack assembly points and patrol lines. This intelligence was fused with other sources, HFDF aerial reconnaissance, to create a stunningly accurate picture of the North Atlantic chessboard. The tool for this new offensive was the dedicated support group, or more aggressively, the hunter-killer group. These were fast, powerful warships, destroyers and destroyer escorts paired with a small aircraft carrier, like the USS Bog or HMS Biter. They were not tethered to a convoy's slow pace. They were wolves set loose to hunt other wolves. Guided by Ultra, they would steam at high speed to intercept known U-boat concentrations. The aircraft from their escort carriers provided the crucial final link: visual sighting and immediate attack, forcing the U-boats to dive and lose their mobility, or destroying them on the surface. The effect was devastating and immediate. The pivotal battle occurred around the slow convoy ONS-5 in May 1943. A massive pack of over 30 U-boats converged, but this time, the escort commander knew they were coming. Through a brutal, fog-shrouded 7-day battle, the escorts, reinforced by a support group, fought with uncanny prescience. Ultra allowed them to anticipate the U-boats repositioning. The result was a massacre, but not of merchantmen. the Allies sank 7 U-boats for the loss of 12. Merchant ships, a catastrophic exchange rate for Durnitz, May 1943 became known as Black May in the U-boat arm. 41 U-boats were sunk that month alone, a loss rate of over 30% of those at sea. It was an unsustainable hemorrhage. The American bomb fleet, growing by the week, ensured this was not a temporary setback. By the end of 1943, over 120 US Navy bombs were in operation. Their sheer processing power allowed Bletchley and Washington to keep pace not only with daily key changes but also with new German naval cipher variants introduced in desperation. The intelligence cycle tightened. U-boats leaving their pens in France were tracked from the moment they reported their departure. Their mid-ocean refueling rendezvous with Milch Cow supply U-boats were pinpointed and attacked, strangling their operational range. The Atlantic, once a German hunting ground, became a killing field for U-boats. The technological shield of Enigma had been nullified by the industrial counterweapon of the bomb, and the tactical consequences were played out in steel and depth charges. The confidence of the U-boat crews, once sky-high, shattered. Morale plummeted as each patrol became a likely death sentence. The happy time was over, replaced by a grim understanding of their own vulnerability. The raw numbers tell the story of a war within a war, decisively won. From March 1943 until the end of hostilities, the Allies maintained a near-continuous read of German Naval Enigma traffic, the American bomb fleet ultimately numbering 121 machines by war's end processed over 2.5 million intercepted messages. Their relentless operation turned the tide of the Battle of the Atlantic with mathematical certainty. Allied shipping losses, which had peaked at over 700,000 tons in November 1942, plummeted to manageable levels by late 1943, while U-boat losses soared. In 1942, the Allies sank 85 U-boats. In 1943, they sank 237. In 1944, as the bombs worked in concert with overwhelming Allied air and naval supremacy, another 241 were destroyed. The Kriegsmarine lost over 75% of its U-boat crews, the highest casualty rate of any service in any major combatant nation. The once formidable wolf packs were decimated, reduced to sporadic, ineffectual raids. Yet perhaps the most remarkable aspect of this victory was its silence. The secret of Ultra was guarded with a fanaticism equal to the Germans' faith in Enigma. Every piece of intelligence was sanitized, given a plausible cover story, aerial reconnaissance, radar contact, a chance sighting. The sacrifice of convoys was sometimes accepted to avoid revealing the source. When the US Navy captured the German submarine U 505 intact in 1944, its Enigma machine and codebooks were seized in a top-secret operation, and the crew was isolated from all other prisoners of war to maintain the illusion that it had been sunk. This monumental deception was a triumph of Allied discipline. The Germans, convinced of Enigma's theoretical inviolability, attributed their losses to improved Allied radar and overwhelming numbers. They tinkered with procedures, added more rotors, but they never fundamentally abandoned the machine. Their faith in technology, unshaken by battlefield evidence, became their greatest vulnerabilities. The strategic legacy of the bomb's victory extended far beyond the Atlantic. The intelligence harvested guided Allied operations across the globe. Ultra revealed German intentions in the Mediterranean, allowing the Allies to ambush Axis supply convoys to North Africa. It provided detailed order of battle information before D-Day, confirming the success of the Fortitude Deception campaign that pinned German forces away from Normandy. It exposed German fears and assessments, offering a direct window into the enemy's mind. The breaking of Enigma shortened the war by conservative Allied estimates by at least 2 years, saving countless lives on all sides. But the legacy was also technological and existential. The bombs, particularly the American hybrid electromechanical electronic models, were direct precursors to the Modern digital computer, they proved that machines could be built to perform complex, logical operations at unimaginable speed. The teams at Bletchley and Dayton, which included pioneers like Alan Turing and the engineers who worked under Joseph Desch, carried this knowledge into the post-war world, seeding the computing revolution. The victory over Enigma was thus a dual triumph. It won a crucial campaign of the Second World War, and it silently ignited the information age that would define the century to come. The machines built to break a cipher became the prototypes for machines that would one day reshape all of human society. The story of the Enigma and the bomb is a parable of modern warfare where victory is forged not only in the fury of battle, but in the silent, relentless friction between intellect and engineering. It was a conflict fought in abstract mathematics, in the precise curl of a wire soldered onto a rotor, in the sweat-drenched silence of a machine room where the only sounds were the whine of motors and the click of a relay signaling a breakthrough. The Germans placed their faith in a perfect lock, a mechanical guardian of secrecy whose complexity they believed was synonymous with security. The Allies, facing annihilation, were forced to evolve a new kind of warfare, one that targeted the lock's logic, not its physical form. In the end, the unbreakable machine was broken, not by a single genius, though genius there was in abundance, but by a vast, interconnected ecosystem of minds, the Polish mathematicians who saw the first crack, the British cryptanalysts who widened it, the American engineers who industrialized the solution, and the thousands of men and women who operated the machines, intercepted the signals, and guarded the world's most dangerous secret. The US Navy Bombe was the culminating instrument of this effort, not a thinking machine, but a machine that could exhaust possibility, turning the enemy's own technological arrogance into a weapon against him. The victory in the Atlantic secured the lifeline of democracy, enabling the immense offensives that would crush the Third Reich, but the deeper victory was epistemological. It demonstrated that no system of secrecy, however elegant, is immune to the combination of human ingenuity and industrial will. It marked the moment when warfare irrevocably expanded into the realm of information, where the control of knowledge became as decisive as the control of territory. The bombs fell silent in 1945. Many dismantled, their very existence classified for decades, yet their legacy echoes in every byte of encrypted data that secures our digital world, a perpetual reminder of the enduring duel between those who build walls of code and those who find the will and the way to see through them.